Should I record my? Okay, so hello everyone. Today I'm going to present Visual Programming, Compositional Visual Reasoning Without Training. This paper was accepted and presented at CVPR 2023, and actually also this paper was awarded to be the best paper at CVPR 2023. So WisProc is a neuro-symbolic approach to solving complex and compositional visual tasks given natural language instruction. And the main aspect of WisProc is that it doesn't require task-specific training at all. Instead, it leverages the in-context learning ability of LLMs to generate Python-like modular programs, which are then executed to get the solution and a comprehensive and interpretable rationale. So we can just give the prompt to the WisProc on some visual task, and the WisProc will automatically generate a program to tackle the proposed task. So let's quickly have an example of this. So a user can feed some instruction to the WisProc, like in here, and so the model decomposes this instruction into program steps like this, and each of these tasks are handled by end-to-end trained models or programs. So in this particular example, the model has to first understand the intent of the query. So this is hiding the faces of some actors, and so to performs these tasks, it should detect the faces and retrieve the knowledge about the actors, and then it should apply some image manipulations to hide their faces. So and in its core, WisProc utilizes GPT-3 LLM to generate the answer. And LLMs such as GPT-3 have shown a remarkable ability to generalize to new samples. For a task having seen a handful of input and output demonstration in context, the key idea of in-context learning is to learn from an analogy. And so in-context learning requires a few examples to form a demonstration context. These examples are usually written in natural language templates. And then ICL concatenates a query question and a piece of demonstration context together to form a prompt, which is then fed into the language model for prediction. But unlike unsupervised learning, this in-context learning does not require gradient calculation for the phase of the training. So here, if this is an example, these two examples are fed into an LLM, and it can apply a generalization on these two examples and generate an output for something it hasn't seen before, or something like this. So WisProc uses in-context learning ability of GPT-3 to output visual programs for natural language instructions. So we can prompt with some in-context WisProc with some in-context examples like this. We prompt some instructions and how these programs will behave, and it can then generate some program based on an instruction it hasn't seen before, but this instruction is an analogy to the ones it has already observed before. So it generates a program by itself without looking at the picture at all. So, and each line of this generated program may invoke one of several off-the-shelf computer vision models, image processing subroutines, or Python functions to produce intermediate outputs. and in VisProc they are called modules. And so this VisProc module is a Python class that has methods to parse the line to extract the input argument names and values and the output variable names, and execute, which execute the necessary computation that may involve trained neural models and update the program state with the output variable name and value. And also it can summarize all of these steps using the HTML. So to extend the VisProc's modules, we just have to use this abstract class and create some techniques in involving these parse and execute steps. So, in addition to performing the necessary computation, each model class also implements a method called HTML, which is used to visually summarize the inputs and outputs of the module in an HTML snippet. So the interpreter stitches the HTML summary of all program steps into a visual rationale that can be used to analyze the logical correctness of the program and inspect the intermediate steps which are involved in the program, as well as the outputs. So VisProc is evaluated across 4 tasks, which include compositional visual question answering, which is called GQA, and zero-shot reasoning on image pairs, factual knowledge of object tagging, and image editing with natural language. Compositional VQA accounts for multi-step visual question answering. So, for example, we can consider a question: is the small truck to the left or the right of the people that are wearing helmets? And VisProc will localize the people wearing helmets, crop the region to the left or right of these people, and check the small truck on the either side and return the correct output for that. And so VQA only answers single image queries, but VisProc can also perform computation on a collection of images. So an example could be which landmark did we visit the day after we saw the Eiffel Tower. So this would require to parse the whole data set of the pictures taken in some, let's say, a trip. And instead of assembling an expensive data set and training a multi-image model, VisProc uses a single image VQA system to solve a task involving multiple images without training on multi-image examples. So it decomposes the complex statement into simpler questions about individual images and a Python expression involving arithmetic and logical operators, and answers the image level question. So, and for knowledge tagging, VisProc uses GPT-3 as an implicit knowledge base that can be queried with natural language prompts. And by using GPT-3, VisProc creates a list of categories, which are then passed to other modules for evaluation. And image editing with NLP accounts for tackling complex instructions like the one we already seen before. And the complexity of this task arises in the identification and object highlighting and replacement in the queries of users. So for GQA, authors evaluated different prompting strategies on the GQA test def set. For the largest prompt size evaluated on the vol set, authors compared the random strategy consisting of the VisProc's best prompt chosen amongst 5 rounds of the validation set and the majority strategy, which takes maximum consensus predictions for each questions across 5 rounds. So the accuracy of the voting strategy was the highest because the voting strategy across multiple rounds it can effectively increase the total number of in-context examples and seen for each prediction. And for the zero-shot reasoning, authors chose to evaluate upon the NLVR benchmark using the NLVR test, and the evaluation strategy is the same as in GQA. So while VisProc performs the NLVR task zero-shot without ever training on image pairs, so it shows strong zero-shot performance using only a single image VQA model for image understanding and an LLM for reasoning. And for knowledge tagging, all instructions require open vocabulary localization and querying a knowledge base to fetch the categories to tag localized objects with. This makes it an impossible task for object detectors alone, but with the original instruction. So VisProc achieves 64% F1 score for tagging, and which involves both correctly localizing and naming the objects, and 81% F1 score for localization alone. So, and since VisProc also can construct the visual rationale, further performance gains could be also achieved by modifying the instructions. And for language-guided image editing tasks, these are like the samples which are fed to the model. And authors report a 60% accuracy upon testing the original instruction, and then after modification, it also gains about 7% increasing its accuracy. So